Good morning, everyone. I'm Dr. Sheetal Rawat. Welcome to this lecture series on classical mechanics. This has been organized by KAAS Academy. Today is the second lecture. In the last lecture, if I just recapitulate everything, what we have done is we have started with a brief introduction about the Newton's mechanics. And then we saw the transition from the Newton's mechanics to the Lagrangian mechanics, how it was done, why it was required, what are the advantages of the Lagrangian mechanics. I started with a very important principle, that is the action principle, which is basically the foundation for obtaining all the equations of motion in classical mechanics, in quantum mechanics, everywhere. Okay. Then what I did was I took a phase space. There I used this action principle and then obtained the Lagrange's equation of motion, or famously it is known as Euler-Lagrange's equation of motion. After that, I told you how this Newton's mechanics, or you can say Newton's famous force law, which is known as F is equals to ma, is obtained. It is also based on the action principle. I told you about the advantages of Lagrangian mechanics, Lagrangian formalism, why it is a superior tool than the Newtonian formalism. Okay, it has its own disadvantages also. That is why there was a shift from the Lagrangian mechanics to the Hamiltonian mechanics. So this is just a recapitulation. I also mentioned yesterday, if you have any questions, I will be taking it today. As I can see, since what I will be doing is, if you have any questions, you can ask me right now. Just 5 minutes for the question session. Then we will start with today's topic, that is the Hamiltonian mechanics. Before that, we will be doing some questions, some problems, how to use this Lagrangian equation of motion, Euler-Lagrange's equation of motion, to solve the dynamic systems. Any questions?
Sheetal madam, are we audible from the classroom?
Yes, sir. Yes, sir.
Okay. Thank you so much.
Hello. Question nahi hai, to should I proceed?
Yes, ma'am.
Okay. See, this was just the recapitulation, as you can see on the screen. Advantages of the Lagrangian dynamics we have done yesterday. Now I have come to the part where what we will do, we will take one system and see how we apply this Lagrangian equation of motion tool here. Okay, so what we will do, this is the general concept. This is general concept. What we do is, first step, in order to solve any problem, what we will be doing, first we will select the identify the generalized coordinates in the system, whatever system we are taking. Then we will be finding out TL, which is T minus U, which is kinetic energy minus the potential energy. And then we will be using Euler-Lagrange's equation of motion. Equation of motion. Okay, so I will be starting with a very simple example, that is your simple pendulum. All of you must have solved this system, that is of the simple pendulum, with the Newtonian mechanics. What today we will be doing is, we will be solving this system using the Lagrange's mechanics. Okay, this is a simple pendulum. As you can see, it's motion, to and fro motion here. I'm assuming it is, the length is inextensible, L. Okay, and this is at any instant of time, it is theta. Now, as I told you how to apply this concept, first thing is you have to identify the generalized coordinates of the system. The generalized coordinate for this system are just theta, because theta, or you can say it has 1 degree of freedom. One more thing to mention, I am taking this in a 2-dimension. Had this been this simple pendulum in 3-dimension, the generalized coordinates will increase automatically. Okay, this is in 2-dimension. That is why the generalized coordinate here are one generalized coordinate, which is theta. As per the definition of generalized coordinates are those quantities which gives you the full configuration of the system. That is why if I know theta, I know everything about the system of simple pendulum. So first step is done. I have identified the degrees, the generalized coordinate, and we know what is the degree of freedom. That is one. Now the second step is you write down this quantity L is equals to T minus V. So what is the kinetic energy of this system? Kinetic energy, it is simple. If m is the mass of the bob, then half m L square theta dot square. We know this. This is the kinetic energy of this. You can totally find out. This will be the kinetic energy. Now writing down the potential energy of the system. For the potential energy, what is important is you have to define the reference point in order to write down the potential energy of the system. Okay. What is a reference you are taking? For example, I'm taking reference here. This is my reference point. This is 0. Okay. So the potential energy of the system will be this difference. Okay. How much is this? How much is this? Anybody? Minus mg L 1 minus cos theta. Okay, this difference I'm finding out. This is your L. This is your L cos theta. So your V is minus mgl 1 minus cos theta. Okay, it will be plus because this is 0 here. So the positive coordinate system here. Positive, positive, negative, negative, since this is 0. Okay, now we have this expression, which is your L, which is half ml squared theta dot square minus mgl 1 minus cos theta. Now the next thing is you write down L is equals to half ml squared theta dot square minus mgl 1 minus cos theta. One more important thing is, even if you change the reference, for example, some other student has taken reference point here, its potential energy will change, its potential energy expression will change, which is what? It will simply be minus mgl cos theta. However, this will not make any difference in the obtainment of the equation of motion. Okay, because we are just changing the reference. It doesn't matter here. That will be taken care in the differentiation part. So using the Euler-Lagrange's equation, that is d by dt del L by del. What is the generalized coordinate I'm taking here is theta dot. This is how the Euler-Lagrange's equation for this system looks like, is minus or equals to del L by del theta. Okay, now finding out del L by del theta dot, it will be what? Del L by del theta dot, it will be m L square theta dot dot. I've taken this left hand side is this, is equals to del L by del theta. It is what? It is how much? Is equals to minus, okay, minus plus mgl sine theta. So this gets cancelled, L, and you will be getting your theta dot plus g by L sine theta equals to 0. This is your equation of motion for the simple pendulum. Okay, again, for the simple harmonic motion, what we will be doing? We will be taking sine theta as equals to just theta. For very small oscillations, that is simple harmonic motion, in order that this system performs simple harmonic motion, the assumption that we take is sine theta is very small, therefore sine theta is equal to theta. Okay, so this is your equation of motion from the Lagranges, Euler-Lagranges equation. Any question? Shall I proceed further if you have any question here? Okay. So simple pendulum we have looked at. I told you how to write the Lagrange for the free particle. This we did yesterday. Now this you can try at home for the inclined plane. Atwood machine we can look at again. What is an Atwood machine? Atwood machine is basically a pulley. Okay. And using an inextensible, I'm assuming that the string is inextensible. It connects two masses, M1, M2. Okay, M1, M2. Now you are supposed to find out. Yesterday I told you you can solve this using Newtonian mechanics. We all know how to solve this using Newtonian mechanics. However, how to apply this tool, this Euler-Lagrange's equation tool here? What we will be doing, again, first step, let's just take full length of this inextensible string is L. First step is you have to identify the generalized coordinates here. Okay, this is your first step. Now, as you can see, these two masses, they are connected via the string. What happens is, if, for example, let me take, this is your x1, this is your x2, this the position of first mass and the second mass. Okay, and we know that this has been given to you. Someone might think that it has two generalized coordinates, correct? X1, X2, then two generalized coordinates. However, if we look at this equation carefully, what do we get? We get the dependency of x1 on x2. If L is equals total length is x1 plus x2, then x1 is nothing but L minus x2. Both are connected. So the independent variable is just one. You can either take x1 or x2, other will be connected. Okay, that is why it has 1 degree of freedom, and the generalized coordinate for myself, I'm taking it as x2. Okay, x1 is just L minus x2. This is so the independent coordinate is only x2 here, which I am considering. So I can change this. Instead of x2, let me take this as x, and this let me take as L minus x. So x is your generalized coordinate. Now I have identified my generalized coordinate. I know what is the degree of freedom of my system. Now moving on to the second step, which is your L. That is L is equals to T minus U. The kinetic energy of the system will be, we know what is kinetic energy. It is half mv square. M V1. For mass M1, it will be V1 square, which V1 is nothing but L minus X whole dot. So instead of this, let me take as, it will be simply X dot square. Okay. It is squared, so minus sign is taken care of. Plus, let me take this M1, M2, again it is X dot square. This is your kinetic energy of this system, or you can simply write as half M1 plus M2 X dot square. Now writing down the potential energy of this system, for that you need to specify what is your reference point. It's 0. Is 0. 0 is here, so it will be minus M1 G L minus X minus M2G X. This is your potential energy. So now you can do on your own also. If I know L, I can plug in this L in the Euler-Lagrange's equation and find out the equation of motion as we did earlier. Okay, the central force problem that I will take tomorrow when we will start with the this full topic on central force. Now spring pendulum system, this you can try on your own. What is a spring pendulum system? Spring pendulum system will be, and instead of this inextensible string, I will be using a spring, and then a pendulum is attached, mass M. Okay, now how to handle this kind of a system? Till now we have seen that the length is not varying. In case of simple pendulum also, it was fixed. Here also, it is fixed. Now what? We will just look at this system. Spring pendulum. This is a spring, and then a mass is attached to it. It is now it is important to note, again I'm talking about in 2D, in a plane. This is not in 3D, okay? So the generalized coordinates here will be, can anybody tell me what will be the generalized coordinates here? How different is this system from the simple pendulum that we have discussed earlier? Length is also changing. To and fro motion, I will just displace it here. Length will also change. That is x-axis, y-axis, both are changing. So what we can do is, let me take the original length of the spring as L, and the displacement, the change in length of the spring as X. Correct? Now, if I will displace this, then it will be somewhat like this. Okay, we know. So instead of just being just having 1 degree of freedom, this kind of a system has 2 degrees of freedom. 2 degree of freedom. Okay, that is the number of generalized coordinate here. Apart from theta, it has x also. Theta and x, 2 degrees of freedom. Degree of freedom. So once we identify the generalized coordinates, we have identified the generalized coordinate, we will proceed in finding out the kinetic energy and the potential energy of the system. Okay, now what we can do, the first method that I will be taking here is, I will be talking in terms of the positions. At any particular instant, the position of this mass is given by x and y. Okay, let me write down the values for x. What is your x here? It will get extended. I'm assuming that it gets extended. Okay, so the x will be L plus x sine theta. Okay, then y will be L plus x cos theta. This is your theta. Okay, now in order to find out the kinetic energy, that is your kinetic energy T, it will be half m x dot square plus y dot square. And you can automatically find out what is the potential energy. T minus V. It is your, if I'm taking this as the reference, this is my reference point, it will be minus mg capital Y, which is your L plus x cos theta. Now you know what is your T, what is your V, and you can find out the equation of motion using Euler-Lagrange's equation. Okay, so these are all the problems that we will be taking. You can find out the Lagrange equation of motion for the double pendulum. What does a double pendulum looks like is just two pendulums. For example, here, then again here, two pendulums. For example, this is L1, this is L2. Two pendulums are attached together. You can use same concept of position coordinates. For this bob, you can take x1, y1. For this one, you can take x2, y2 and find out the Lagrangian and then the corresponding equation of motion. Okay, these are all the problems you can, these are all the examples where you can apply the Lagrangian. In fact, there are many more systems. You can look for them in the books that I've mentioned earlier in Goldstein, in Landau. In all these books, you can find out many more problems and try to solve them. Okay, so today let's just come. Now we will be starting with the second topic today, which is the Hamiltonian mechanics, Hamiltonian dynamics we'll be talking about. Now, let's just recapitulate, as I told you yesterday, what are the disadvantages of the Lagrangian mechanics. First very disadvantage is that it is a second order differential equation which is difficult to solve. It would have been much better if we have a first order differential equation which is much simpler than the second order differential equation. Okay, that was the first disadvantage. So Hamiltonian takes care of that. Here the Hamilton's equations of motion that we will be obtaining, they are first order differential equation. They are much simpler to solve. Okay, that disadvantage is taken care of. Second one was it is not easy to solve, but it is not easy to quantize using Lagrangian, Euler-Lagrange's equation. So again, Hamilton's equation of motion, they can quantize. We can quantize using Hamiltonian dynamics. Okay, we all know in quantum mechanics, we use Hamiltonian and then find out the quantized systems. That is a very good example. So these two disadvantages are taken care of here. Now, the question is how to transition from Lagrangian to the Hamiltonian dynamics. What was done in order to transition from the Lagrangian dynamics to the Hamiltonian dynamics? What was done? So what was done was a Legendre transformation was performed on the Lagrangian function to obtain the Hamiltonian function. I don't know if you all know what a Legendre transformation is. Let me just brief you about the Legendre transformation first. Okay. Legendre's transformation. This was performed on the L. L, we know it is a function of generalized coordinate, generalized velocity, and function of time. It was performed on L, this function, so that we can obtain Hamiltonian function, which will be a function of generalized coordinate and its conjugate, that is the generalized momentum and time. So what is Legendre transformation? That answer I have answered here. It is when you transform a function from one variable. For example, this is a function. I'm transforming it from here to, I'm transforming it to H, that is the Hamiltonian function, which contains the conjugate of this. So let me tell you, conjugate basically means, okay, now question is, what do you mean by the conjugate? Conjugate is basically the derivative. For example, if, or in another word, let me give you, conjugate means if the Poisson bracket of two variables Q, P is 1, that means Q and P, they are conjugate to each other. This is in mathematical form. Let me give you another example. Let me give you another description. Another description is two variables are conjugate to each other when, for example, it is Q, when the other variable, that is P, will be the derivative of a function with respect to which I'm taking the conjugate. We all know that momentum is given by del L by del Q dot. Okay. Action integral is the derivative is this. This is basically, okay, this is all mathematical, but just all you keep in mind is this one. The Poisson bracket of the two variables is 1. That means they are conjugate to each other. Here I know that my momentum, generalized momentum, is given by del L by del Q dot. We know this is my generalized momentum. So the Legendre transformation converts one function into another function, which is a function of its conjugate. So only change here is instead of Qi dot, we have Pi. Where Qi and Pi, they are conjugate to each other. This is how the transition from the Legendre function, from the Lagrangian function to the Hamiltonian function was done using Legendre transformation. Okay, so now we have another function, that is the Hamiltonian, which is a function of Qi, Pi, and time. What we will be doing is we will be obtaining the Hamilton's equation of motion. What we did, we know what L is, then we obtain the Euler-Lagrange's equation of motion. Same thing we will be doing here. We will be obtaining the Hamilton's equations of motion. before that, let me give you a brief about the generalized momentum. As I told you, the generalized momentum is given by del L by del Q dot. Q means any generalized coordinate. You can take Cartesian coordinate, you can take spherical coordinates, cylindrical coordinates, all on you, depending on your convenience. Okay, there is one more term which is often used in Hamiltonian mechanics. It is the cyclic coordinate. What do you understand by a cyclic coordinate? Cyclic coordinate is that coordinate which is absent, that generalized coordinate which is absent in the Lagrangian. Whatever is the Lagrangian that I'm talking, if a generalized coordinate is absent, then that coordinate is known as a cyclic coordinate, also known as the ignorable coordinate. Okay, this is of very much importance because if there is a cyclic coordinate present, there is a cyclic coordinate. If you identify the cyclic coordinate, then what we do is corresponding momentum, cyclic coordinate, the momentum corresponding to the cyclic coordinate, or you can say the conjugate momenta, its derivative, you can say dp by dt is 0, or you can say its conjugate momenta is a constant of motion. This has a very deep meaning. Okay, this is all mathematical right now, but this concept is used so at so many places. Okay, using this concept, you can find out how your you can apply this in conservation of momentum, conservation of linear momentum, conservation of angular momentum, then conservation of total energy. You can apply this concept of cyclic coordinate and find out these conservation principles. Then it becomes very easy when you apply the cyclic coordinate systems. Okay, ignorable coordinate. Now moving on to how to derive the Hamilton's equation of motion. Okay, before that, before deriving the Hamilton's equation of motion, I would like to point out something. We know that Hamilton, it is a function of pk, qk, and t. That is your generalized coordinate, generalized momentum, and time. Now what was done was, this expression was obtained using the Jacobi's integral. That is the expression. I'm not going into the derivation part. All I will be doing is I will just write down the expression that was obtained. H was found out to be this. This is the expression that was obtained, that your Hamiltonian is summation P Q dot minus L. If I'm writing K here, that will be K1 to N, depending. This is N is your degrees of freedom. This was the expression for the Hamiltonian that was obtained. Okay, using this, we will be finding out the Hamilton's equation of motion, like the Euler-Lagrange's equation of motion. Okay, now moving on here, Hamilton's equation. What we will be finding out? We will be finding out these two very, very important equations, Hamilton's equation of motion. These two, 1 and 2. So let me just brief you about it, how to obtain this equation. All we will be doing is, we should know what variables H depends upon and on what L depends upon. So first, taking the differential of H, we know H depends upon the generalized coordinate and the generalized momentum and time. This is how I can write my DH. Similarly, I will be writing my DL. and then plugging in the value of h. H, I told you, it is your summation of p q dot minus L. So finding out, plugging in the value of dh, dl here, and summation of p q dot, and then comparing the coefficients, we get the famous Hamilton's equation of motion. These are very important. First equation of motion is q dot is equals to del h by del p. Second equation of motion is t dot is equals to minus del h by del q. Now, another thing I would like to point out is it has momentum. It has momentum. And your p dot is dp by dt. So these very well apply to dynamic system also. Dynamic system. So they make our life easier when we use Hamilton's equation in solving for the dynamic systems. Okay, so these are your Hamilton's equations of motion, which were obtained like this. Okay, now I will be taking just one example, that how you apply the Hamilton's equation of motion for finding out the equation of motion. Hamilton's equation for finding out the finding out the equations of motion. These are the Hamilton's equation in different coordinate system. For example, in the Cartesian, if I'm taking a system that is a Cartesian coordinate system, what will be my T there? That is your kinetic energy. It will be half m x dot square plus y dot square plus z dot square in 3 dimension, if I say. Okay, in a Cartesian coordinate system, it will be T will be half m x dot square plus y dot square plus z dot square, and your V will be, it will be a function of x, y, and z. This is for the Cartesian coordinate. That is a free particle in 3 dimension. I'm saying this is my Lagrangian. In other words, this is my Lagrangian of a free particle in 3 dimension. If I'm taking my generalized coordinate at the Cartesian coordinates. Now, for the same thing, if I represent my system, as I told you, I will be taking just one example. That example is a system of a free particle. If I want to represent my system, same system in the polar coordinate system, then my Lagrangian will simply be what? L will be equals to half m r dot square plus r square theta dot square. This will be your Lagrange. No, not just this is your kinetic energy minus v r comma theta. This will be your Lagrangian for a free particle expressed in polar coordinate system. If I'm taking my generalized coordinate in the form of polar coordinates. Okay. Now these are the Lagrangian. I can, in order to write down the Hamiltonian, we have to do some rearrangements. Okay, we have to do some rearrangements. How you will be doing some rearrangement and why these rearrangements are required? Because my Hamiltonian, it is a function of generalized coordinate and the conjugate momenta and t. That is why I cannot express my Hamiltonian in r dot. This is your in r dot and t. Two generalized coordinates here, so it will be r dot t, theta dot t. Okay, now one more thing I would like to point out here is, as you can see here, there is one cyclic coordinate. Which coordinate is missing? As you can see, we have r dot. Okay, now we do not have theta here. However, we have theta dot. So what is the cyclic coordinate? The cyclic coordinate is theta, which means its conjugate momenta, will be p theta. It will be a constant of motion. It will be constant. Okay. Now, similarly, you can extend this example of free particle in cylindrical and spherical coordinate. Now, let me come back to second. How to find out the Hamiltonian if you have L given to you. L is equals to, for the polar coordinates, I am taking m r dot square plus r square theta dot square minus v r comma theta. Okay, this is your L. Now H will be equals to, we know, summation of k equals to 1 to n p r p qk, you can say qk dot minus L. Plugging in the values, how many generalized coordinates are there? 2 generalized coordinates, which are r and theta. So plugging in the value, we know this is, for example, let me add p r dot plus p theta dot minus L. L is half m r dot square minus half m r square theta dot square plus v r comma theta. This is your H. So what I will be doing is, I will be utilizing this concept, that is your P r is equals to del L by del, PR is equal to del L by r dot. This is the definition of conjugate momenta. Similarly, for P theta is equals to del L by del theta dot. Now, plugging in the values, this is your L, find out del L by del r dot. Then for P theta, this is your L, find out del L by del theta dot. Okay, now we will be doing your PR comes out to be del L by del r dot. It is your simply m r dot. Similarly, your P theta will be del L by del theta dot, which is your m r square theta dot. Now what we will be doing is, we will be eliminating your r dots and theta dots. So your r dot is simply PR by m. Your theta dot is simply p theta by m r square. Now what we will be doing here is, we will be plugging in the value of r dots here, theta dot here, and we'll be getting rid of q dots. Now whatever expression we'll be getting, that will be your Hamiltonian for the system. Am I clear? Let me write down the Hamiltonian also, then will be a better example. Okay, so this will be your Hamiltonian. H is equals to 1 by 2m p r square plus p theta square by r square plus v r theta. This was obtained when I plugged in the values of r dot and theta dot, getting rid of r dots and theta dots from the Hamiltonian part, because I want my Hamiltonian as a function of your generalized coordinate and your generalized momenta, that is your P. comma t. Okay. Any question in the Hamiltonian dynamics?
No, ma'am.
No question? Okay, let me give you a question. Let me give you a problem. You do that. Okay, let's just take a simple pendulum problem. Now, what you do is, we have done this simple pendulum problem, right? This one. We know what is the L for a simple pendulum. We know what is the equation of motion for a simple pendulum. Now, your classwork is find out this equation of motion using Hamilton's equation of motion. This equation of motion was obtained using the Euler-Lagrange's equation. Now you find out this equation of motion using Hamilton's equation of motion. So what are the Hamilton's equations of motion? Q dot is equals to del H by del P. P dot is equals to del H by del Q minus. This is very important. Use these Hamilton's equations of motion. Hamilton's equation of motion and find out the equation of motion of a simple pendulum. Simple pendulum. You know what is the L for a simple pendulum? Okay, all you have to do is you have to find out H for a simple pendulum. I told you how to do that. And then using these Hamilton's equations of motion, you have to find out the equation of motion for a simple, that is theta dot plus G by L sine theta, or you can say simply equals to theta equals to 0. Do this right now. If you have any problem, you can ask me. And that is all for today. Just do it. Done?
Yes, ma'am. Yes, ma'am.
Okay, everybody could able to do that?
Yes, ma'am.
Okay. Okay, so that is all for today. Tomorrow we'll be starting with the central force. And I will be sharing the PPTs today itself. Sorry, I could not do earlier. Today I will be sharing the PPTs. Okay.
Thank you, ma'am.
Thank you. Thank you, everyone.